Good evening students, welcome to Study Spectrum. I am Rapen Patel and I welcome you to study concepts of physics with me. We'll begin with our very first chapter of the syllabus, that is electrostatics. It's one of the difficult chapters as well as very important from exam point of view, and conceptually this is a good chapter. Now, to begin with, let's see a question. Here you can see an object. Question is whether I can exert a force, maybe pull or push, on this object without coming in contact with it. I'll not touch it directly or with any third object. So can I exert a force on it? For me, it's not possible. But then question is whether any other machine or some objects, if have some properties, can exert force on any other object without actual contact. The answer is yes. While learning mechanics previous year, you would have heard a word, non-contact forces. So there are few forces in nature which are non-contact forces, and one of them you have studied last year, gravitational force. The two objects in universe having some mass separated by a finite distance can exert force on each other. One of them will attract the other, or the second object will attract the first by virtue of gravitation without actual contact, right? And the next in the line is electromagnetic force. First we have studied in 11th standard, that is gravitational force, where contact between the bodies was not required to exert force. And the next in line is electromagnetic force. Basics of it we have studied in junior classes, but here again we'll start from basics, right? To begin with, let's ask few questions. Since childhood we have seen lightning during thunderstorms, or we have experienced crackle sound and say maybe small sparks when we remove our woolen clothes or we wear woolen clothes, especially during dry weather. Again, sometimes you would have experienced when you walk through a carpeted floor and immediately touch a metal doorknob, you feel a quick shock and we wonder what was that. After studying this chapter in detail, or concepts of electrostatics in detail, you'll be able to answer these questions. These are not very difficult questions now. So let's go back to historical development of electrostatics. Today we talk about electric field, electric charges, electric potential, electric flux, Gauss law, and many other things. But from where this started, from where we have derived or concluded these terms, how we have defined these terms. So let's go back to history. Around 2600 years back, maybe in 600 BC, around 600 BC, Thales of Miletus from Greece had known a fact that a material called ember, when rubbed against wool or silk cloth, acquires an ability to attract light objects, maybe small pieces of paper or say polystyrene balls or pith ball, something like that. So when ember was rubbed against silk or woolen cloth and was brought closer to light papers, small pieces of paper, it was observed that it gains or acquires an ability, that ember acquires an ability to attract that paper. Later on we came to know that not only ember and silk, there are many other objects, pair of objects, which when rubbed against each other acquires ability to attract light objects. Examples are plastic, say glass, and many other are there. I'll call them bad conductors. Why bad conductors? I'll come to it later on. In fact, the word electricity which we use today commonly, the word electricity, has been derived from the word electron, which actually meant ember. So electricity word itself is derived from that concept. Ember, which means electron. The word electricity is derived from there. So now let's see a series of experiments which helped our physicists to draw some important conclusions. A plastic rod was rubbed against wool, and after doing that, the two plastic rods, again after rubbing against wool, were brought closer to each other, and it was observed that they repel each other. Whereas at the same time, the two strands of wool which were rubbed against plastic rod were seen to repel each other. But the plastic rod, when was brought closer to wool, plastic rod had attracted wool. Now, the material was changed. Instead of plastic, they had taken glass. Once again, they had rubbed glass against that wool fiber and repeated the experiment. The two glass rods, after rubbing against wool, were brought close to each other, and it was observed that they repel. The glass rods repel, whereas the similar thing was observed in wool fiber or strands of wool. Once again, but when the glass rod was brought closer to the wool strand, glass rod was seen to attract wool. Then again what they did, plastic rod and a glass rod were rubbed against wool and then were brought closer to each other. The plastic rod this time was seen to attract glass rod, whereas the two glass rods, when they were brought closer to each other, were seen to repel. But glass rod and plastic rod were seen to attract each other. So what our scientists or physicists have concluded from there, the first thing, that there must be exactly two types of entities which have ability to exert force on each other, maybe attract or repel, without any physical contact. There must be exactly two types of entities which have ability to attract or repel each other without any physical contact. This was the first thing they have concluded. Then next they concluded that this entity must be present. In fact, both the type of entities must be present in every object. Let it be silk, let it be wool, let it be plastic, let it be glass, or even human skin. So the two type of entities must be present everywhere, in every substance or every object. Then when glass rod was rubbed against silk, glass would have acquired one type of entity, to which we say one type of charge, and silk acquired another type of entity, that is another type of charge. Similarly, when plastic was rubbed against wool, plastic acquires one type of charge and wool acquires another type of charge. And if you remember, we have seen glass rod attracts silk, whereas glass rod repels glass rod. So the two glass rods have same type of entity, same type of charge, and they were seen repelling each other, whereas silk and glass had different type of entities or different type of charge and were seen attract each other. So they made a conclusion that similar charges or similar entities repel each other, whereas unlike charges or dissimilar entities attract each other. Right? So this was the most important conclusion here. I'll summarize it again. There must be exactly two types of entities which have ability to exert force on each other without any physical contact, and the two entities were named as two charges, right? Then similar charges repel each other, and dissimilar charges or unlike charges attract each other. And these entities, that is charges, both the type of charges, must be present in every object. Okay? So now I'll say, when the two objects are rubbed against each other, as we have seen in glass and silk and all, we'll say the two objects becomes charged. Actually, what would have happened is, one of them would have gained one type of charge and the other would have gained other type of charge. So I'll say they become charged. Now, when glass rod was rubbed against silk, and a plastic rod was also rubbed against silk, and then were brought closer to each other, they were seen to attract each other. Moving further, if the two rods were brought in contact and then separated, when the two rods were brought in contact and then separated, they lost the ability to attract each other. So what would have happened? Maybe something like this would happen. The two rods which have acquired different charges, when were brought in contact, the two charges would have cancelled each other. So I'll say they become neutral, or they lose their charge, or their charges were cancelled. This looked similar to if I add a positive number with a negative number, of course of equal magnitude, they cancel each other, they nullify each other. If I add +3 with -3, answer is 0. So this analogy would have helped our American scientist Benjamin Franklin to conclude that one of the charges is positive and the other is negative. In fact, he has named them as positive and negative charge. Right? And by this convention, following the positive and negative convention, when glass rod was rubbed against silk, glass acquires positive charge and silk acquires negative charge. Whereas when plastic was rubbed against silk, plastic acquires negative charge and silk acquires positive charge. So I'll summarize with these series of experiments, and we can conclude that there are two types of entities which have ability to attract or repel without any contact. They were named as charges. One of them was named as positive charge, other was named as negative charge. Like charges repel, unlike charges attract. These charges were present in every object. These charges were present in every object, and when the two objects are rubbed against each other, to which I'll call insulators for now, later on we'll see why the word insulator, were rubbed against each other, one type of charge gets transferred to the other, and we say both of them becomes charged or electrified and gain an ability to attract the other one. One of them gains ability to attract the other one, and the agency which helps the glass rod and silk plastic rod to do so is known as electricity. The agency which helps glass rod and silk rod to attract each other is known as electricity. And since this electricity was produced by friction, the electricity is also known as frictional electricity.
No more spending your energy and money on coaching classes, or missing classes for rain, for rally, and any other nonsense. Subjects covered by multiple teachers with repeat telecasts. Doubts, concepts, applications, no problem. All explained through great and significant animation. sit back comfortably in your home and watch Study Spectrum TV channel.
So after these many years, now we have better explanations to what we have observed in the previous explanations. And the explanation goes like this. Every object or every substance is made up of atoms. And what constitutes atom? Atoms are made up of electrons, protons and neutrons. These fundamental particles, electrons and protons, have charges in them. So God has given charges to only two fundamental particles, one is electron, another is proton. By our convention, the convention which we have made, electron has negative charge and proton has positive charge. And the magnitude of charge on both of them is same. So, charge on electron is negative and say some value, let us say minus E, and charge on one proton is positive and magnitude is same, say plus E. So, what is the charge, sum of the charge on one electron and one proton? 0. Every atom or every object which is electrically neutral, is not electrified as we have seen earlier, has same number of electrons and same number of protons. But due to some reasons which we'll discuss later on, the objects, some objects have more affinity for electrons. They have tendency to gain electrons, whereas few objects have lesser affinity for electrons. So when two such objects are rubbed against each other, as we have seen in glass and silk, actually some electrons of glass rod had shifted to silk. So now silk has more electrons as compared to protons. So we say it becomes negatively charged. It has more number of electrons now. Silk has more number of electrons as compared to earlier case when number of electrons were balanced by number of protons. So silk has gained more electrons, so it becomes negatively charged. Whereas these electrons were transferred from where? Were transferred from glass. So now glass has deficiency of electrons. Number of protons is more than number of electrons. So glass rod has acquired positive charge, right? So what was happening here? When glass rod was rubbed against silk, some of the electrons of glass rod have shifted to silk, making it negatively charged, whereas glass rod has lost few electrons. So number of protons is more than number of electrons, which makes it positively charged. And positively charged object repels positively charged object, whereas attracts negatively charged object, right? Here is few list of objects which have different affinities for gaining electrons. Like list is dry human hand, then comes glass, human hair, silk, paper, wood, amber, polyester, plastic, PVC and Teflon. So this is a series of increasing affinity for electrons. So if you rub any of these two objects against each other, depending on whether it has more affinity for electron or less affinity, electrons are transferred from one of them to the other. For example, if you rub glass with human hair, glass has lesser affinity for electrons. So glass will lose some of the electrons to human hair, leaving more electrons on human hair and deficiency of electrons in glass. So glass acquires positively charged, positive charge, and human hairs acquire negative charge, right? Now let's move to our next topic, that is insulators and conductors. Question is, when every object has electrons and protons, maybe same in number, in fact same in number, then why anything is said to be a good conductor and why anything is said to be a bad conductor? See, non-metals, especially non-metals, have more affinity for electrons, or we say electrons of non-metals are tightly held towards their nucleus, are tightly bounded towards the nucleus. So they are not available for carrying charge from one point to other, right? But in the case of most of the metals which have lesser electron affinity, they have their electrons loosely bounded to their nucleus. I'll repeat, good conductors have their electrons loosely bounded towards their nucleus, which makes them available for carrying charge from one part to the other, or which helps in transfer of charge, to which we say is conduction of electricity. So good conductors have free electrons. I'll repeat, good conductors have free electrons, but that doesn't mean they have excess electrons. Number of electrons is still same as the number of protons. Overall, good conductor also has net charge equal to 0, whereas insulators also have net charge 0. But electrons of good conductor are loosely held towards the nucleus, loosely bounded towards the nucleus, which makes them free for conduction of electricity. In fact, the better explanation we'll see in coming chapters. But for now, bad conductors I'll say, or insulators I'll say, are the ones which have their electrons tightly bounded towards their nucleus, hence not available for conduction of electricity, whereas electrons of good conductors are free, relatively free, so they can participate in conduction of electricity. So that makes most of the metals good conductor and most of the non-metals bad conductor. Okay. So now moving to the next topic, that is charging. Normally every object is electrically neutral. Why? Because it has same number of electrons and same number of protons. Number of electrons equals number of protons. So net charge on any object is 0. So we say it is electrically neutral. Now, charging means what? Either giving it some excess electrons, extra electrons, so that electrons outnumber proton, making it negatively charged, or taking out electrons so that protons outnumber electron, making it positively charged. So charging means what? Either adding up some electrons or removing some electrons. Adding up electrons means making it negatively charged. Removing some electrons means positively charged. Okay. Now, one of the methods of charging we have already seen, and that is by friction. But that is limited only to insulators. Question is why? If you try to reduce charge or charge any conductor by friction, what happens? Conductor has lot of free electrons. So if you rub it against an insulator or say against other conductor, some of the electrons may get transferred to insulator, but very next moment they will again come back to the conductor. And the reason is, when some charge is left on a conductor, the charge spreads out inside a conductor. Whereas if you consider a bad conductor, if some charge is given on one part of a bad conductor, that charge remains there, right? So if you see here, if a conductor is rubbed against an insulator, there is a possibility that few of electrons may move out to insulator, which is bad conductor actually. But this positively charged, or the positive charge which is left on the conductor, gets uniformly distributed on the conductor, and very next moment it pulls up the electrons which were donated to or which were transferred to the bad conductor and again becomes electrically neutral. So we cannot charge a conductor by friction. Then question is whether there is any other process. So the next method is charging by induction. We use the method of induction to charge good conductors. You can see an example here. In the first case, when two spherical conductors are in contact and a positively charged material or positively charged conductor, a third conductor, is brought closer to them, electrons of the one of the spheres get attracted to the third positively charged conductor. So on left conductor you can observe electrons are pulled up, leaving positive charge on the other one. So left sphere which is in contact acquires more electrons, whereas the second one which is away from this third conductor which is positively charged acquires, or there is deficiency of electrons, leaving it positively charged. Now before you remove this third conductor, separate these two identical spheres or spherical conductors and you remove the third one. So what you see here is the left sphere is left with excess electrons. That means it becomes negatively charged. And the right one, which has deficiency of electron, is left with positive charge. So one sphere has become negatively charged and other sphere has become positively charged. Right? Other way of doing the same thing, a similar thing. Suppose I have only one sphere which I have to charge. As we had two in the previous case, I have only one sphere to which I want to make, say, positively charged. So what I'll do is some source of negative charge I'll bring closer to the sphere or conductor, and simultaneously I'll connect the sphere or conductor to ground. So what will happen? This negatively charged conductor repels the electron of neutral conductor, and now since it is connected to ground, some electrons will move out to ground. Some of the electrons will move out to ground. So what you see here, that some positive charge is left on the conductor. Now before moving this negatively charged conductor, you disconnect it. You remove the connections from ground and now remove the negatively charged conductor. So you will notice that the sphere or the spherical conductor which was neutral earlier is left with a positive charge, right? And some of the electrons of this conductor has moved to ground, right? So this is the way how we can charge a conductor, and this method is known as induction. Explanation for the same you will see in coming topics why this happens. But for now, I know how to charge a conductor by method of induction, right? So now after understanding what charge is, let's discuss few properties of charge. The very first of them is additivity of charges. Question is how to add charge. Question is how to add charge. For example, if there is a conductor which carries some charge, say 5 micro-coulomb, what if I give it 3 micro-coulomb more? What will be net charge left on the conductor? Or if I give it minus 2 micro-coulomb charge, then what will be the net charge left on the conductor? So charge like mass is a scalar quantity. When I say there's a table on which I have placed 5 kg mass, again I have placed 3 kg mass on the table, so I'll simply say that's total 8 kg on the table. If I remove 2 kg from that, what is left on the table? 6 kg. So like other scalar quantities, charges can also be added. If a conductor is given some charge, let's say its magnitude is 5 microcoulombs, and if you give it further 3 microcoulomb charge, so its total charge left on the conductor 8 microcoulomb. However, charge is slightly different from mass. Mass we never say is positive or negative. Mass is just matter stored in the substance. Whereas charges may be positive or may be negative. In fact, we have two charges, one is positive and the other is negative. So, while adding charges, we'll use the word algebraic sum. That means considering their algebraic sign also. 3 kg and 2 kg will always make 5 kg. But 3 microcoulomb and 2 microcoulomb may not be 5 always, if one of them is negative. So what we have to do here is, we have to consider algebraic sign. So plus 3, if there are two charges, you can see here, there are two conductors, one of them carries 3 microcoulomb and the other carries minus 2 microcoulomb. By any means, if I transfer minus 2 microcoulomb to first conductor which carries 3 microcoulomb, the total charge or the net charge left on the first will be plus 1 microcoulomb and not 5, right? So what we have to do is, we have to consider algebraic sign of charges while adding them. Rest, it's same as adding other scalar quantities, right? So how to add charges? Charges can be added like other scalar quantities. The only thing is, you have to consider their algebraic sign, right? So plus 3 and minus 2 together will give you 1 microcoulomb. Okay. So this is your first property, that is additivity of charges. That is how to add charge. Next important term is conservation of charge. Conservation of charge. We have studied this term with other physical quantities like conservation of energy, conservation of momentum, conservation of angular momentum. Now, I'll state conservation of electric charge. The statement goes like this: the total charge of an isolated system will always remain constant. I repeat, the total charge of an isolated system will remain constant. Suppose we have two isolated spherical conductors or conductors of any shape. Initially one of them has plus 5 microcoulomb and the other has minus 2 microcoulomb. So what's the total charge on them? Add them. What is the total charge? 5 minus 2, that is 3 microcoulomb, right? So the total charge of this isolated system plus 3 microcoulomb. Now you do one thing, connect them using some conductor or directly bring them in contact. What will happen? Some of the charge will move from here to there or here to, from the second conductor to the first conductor. And suppose the two conductors are identical in all respect. So finally what is left on both of them is 1.5 and 1.5. Earlier plus 5 microcoulomb was there on the first conductor and minus 2 was there on the second conductor. Together there was plus 3 microcoulomb. If you join them or you connect them or you bring them in contact, some charge gets redistributed. Some of the electrons will transfer from the second to first and so on. After some instance you will see, if they are identical, both the conductors acquire same charge, and that is plus 1.5 plus 1.5. Whatever. What is the total left? Total is still 3 microcoulomb. So do whatever you want. If this is an isolated system, the total charge will remain constant. Of course, if you bring it something from outside, then the total charge may change. But if the system is isolated, then the total charge remains constant. In some of the natural processes, it is seen, especially in radioactivity, that neutron splits up into a proton and electron. So it appears earlier there was no charge, but charged particles were created But whatever the case be, if it is a neutron, what is the net charge on it? 0, as it is electrically neutral. It splits up into a proton and an electron. Proton has suppose plus E charge and electron has minus E charge. Together it is still 0. So statement goes like this: total charge of an isolated system remains constant. Charge can neither be created nor be destroyed. It can only be redistributed among the conductors or particles of that isolated system. There was a negatively charged conductor, there was another conductor which had some different charge. If you connect them, some charge will get redistributed, but net charge or effective charge of the system remains constant. Right? So this was your second property, that is conservation of charge. Now next very important property is quantization of charge. I'll read the word again. Quantization of charge. What does this word quantization means? Quantization means what? Things are not continuous. Things are not continuous. They are in small packets or bundles or something like that. I'll take a real life example. Suppose I ask you to get some tea bags or say some amount of say tea. You go to a shop and ask for a tea which is available in packets. It's available in packets, and the smallest bundle, smallest packet of tea bag is of 50 grams. Smallest bundle or packet of tea bag is of 50 grams. So my question is, can you get 25 grams of tea? No, because smallest packet is of 50 grams. So what you are going to get is 50 grams tea. Suppose I want something more than 50, slightly more than 50. Can I get? No, I cannot get any amount of tea. I'll have to buy 50 grams. The next what I'll get is 100 grams. What next I'll get is 150 grams. I cannot get 125 grams or 110 grams. Why? Because smallest packet is of 50 grams, and what I can buy is multiple of those measures. 50 gram, one more 50 gram, one more 50 gram. So I can buy only multiples of 50 gram. Similar thing happens in the case of charge. We cannot accumulate any amount of charge on a conductor. Whatever charge is accumulated on a conductor is actually integral multiple of charge on one electron. For an instance, suppose I say charge on one electron is 1 unit. Whatever that unit be, charge on one electron is 1 unit. So what I'll get is 1 unit, then next I'll get is 2 units, next I'll get is 3 units, 4 units, and so on. Let us mark it as E. Charge on electron as E. So what charge I can collect or accumulate is E. The next I can collect is 2E. Next I can collect is 3E, 4E. But I cannot have fractional part of E. I cannot collect 10.5E. 10.5 times of charge on electron. Right? So whatever charge, say Q charge, is accumulated on a conductor, then the value Q, the amount of the charge Q, has to be equal to some integer times of charge on one electron. So I'll state, if E be charge on one electron and Q be some charge accumulated on the conductor, then Q is n times of E, where n is some integer. And this concept is known as quantization of charge. Flow of charge is not continuous. Charge is transferred in form of packets. the smallest possible charge is charge on one electron. In fact, the value is 1.6 into 10 raised to minus 19 coulomb. So smallest possible charge is given on an electron, and the flow of charge will be in the form of electrons only. One electron is transferred, one E is gone. Then next electron is transferred, 2 E is gone. Next one electron is transferred, 3 E is gone. But we cannot have 3.5 times of E. So quantization of charge means what? Transfer of charge is not continuous process, it's in form of packets. And the smallest packet available is the charge on one electron. So whatever charge is accumulated on any conductor is simply integral multiple of charge on one electron, and this property is known as quantization of charge. Now our next topic is measurement of a charge. Charge is a physical quantity and we can measure it. SI unit for measurement of charge is coulomb. 1 coulomb we can define using Coulomb's law as 1 coulomb is the charge which, when separated by a distance of 1 meter from other equal charge in space, exerts a force of 9 into 10 raised to 9 Newton on the other one. I repeat it. 1 coulomb charge is the charge which, when separated by another equal charge in space by a distance of 1 meter, exerts a force of 9 into 10 raised to 9 Newton on the other. So that is what we say is 1 coulomb, which is SI unit for measurement of charge. Now 1 coulomb is practically a very large charge. Normally we don't deal in that large charge. Normally what we will see, the magnitude of charge which we'll be dealing in will be of the order 10 raised to minus 3 coulombs, that is 1 millicoulomb I'll say, or say 10 raised to minus 6 coulombs, to which I'll say is micro-coulombs. Let's understand how many electrons would accumulate a charge of 1 coulomb. Charge on 1 electron is 1.6 into 10 raised to minus 19 coulomb. So how many electrons would accumulate 1 coulomb charge? Say n. So n times of 1.6 into 10 raised to minus 19 is equal to 1. So what is n? 1 upon 1.6 into 10 raised to minus 19, which is approximately 6.25 into 10 raised to 18, which is a very huge number. So 6.25 into 10 raised to 18 electrons make 1 coulomb. So 1 coulomb is very huge charge. It's very difficult for us to store it in spaces available with us. What we'll deal is with, say, a few micro-coulombs or millicoulombs at the max, right? Then there is another unit of charge, CGS unit, that is stat coulomb or ESU. How 1 stat coulomb is defined or measured? 1 stat coulomb is that charge which, when separated by equal amount in space by 1 centimeter distance, will exert force of 1 dyne on the other. I'll repeat. 1 ESU or 1 stat coulomb is what? The charge which, when separated by equal amount in space by 1 centimeter, exerts a force of 1 dyne on the other. So you can see the conversion, it's simple. We can claim that 1 coulomb is 3 into 10 raised to 9 stat coulomb. I'll repeat. 1 coulomb is 3 into 10 raised to 9 stat coulomb. You can see the calculations here. Okay. Now, moving to next. One more unit is there which is not commonly used, that is CGS electromagnetic system of units. The charge is measured in EMUs or ab coulomb, and 1 ab coulomb or 1 EMU is 10 coulombs. 1 amp coulomb is equal to 10 coulomb, or which can also be written as 3 into 10 raised to 10 stat coulomb, right?
Choose the right kindergarten, a right bag, and matching bottle to go with. The right school, the right friends. Choose the right subjects and score well. Be an expert in all. The right teacher, and make sure that they like you. Choose the right timing, the right bus, and take a cab if getting late. The right train, and don't stand near the gates. Mind the pockets. Better get into ladies' compartment. And make sure your mustache hasn't started coming. Choose the right study time and forget games. IPL, IHL, rock and metal, guitar, axe. The right group, and be a model to your brother. Seriously. Choose the right syllabus, the right test paper. Keep guessing questions for exams. Choose the right branch, the right college, the right stream. Choose the right career. Lucky to have a father's business to take care of and a father to allow that. The right counselor, the right form, and make sure the project is submitted on time. Choose the right website and rely on your friends for more information. Oblivious of the sites they have been to, there is no end to your woes. Getting better with every step you climb up the ladder. The summer vacation shorter, the bucket list bigger. The night darker, the books heavier. The only light you have is your friends ahead of you. Probably he is right. Ever thought how he got the direction? No more spending your energy and money on coaching classes. No more missing classes for rain, rally, and nonsense. Get your interest back in subjects through our creative ways of teaching. Doubts, concepts, applications, all explained through one vibrant animation. Subjects covered by multiple teachers with repeat telecasts. Special programs only for basic foundation and paper analysis. Personality development, career counseling, admissions, hobbies, all covered. A new approach to study with long-term perspective. So sit back comfortably in your homes and watch Study Spectrum TV channel.
Now, before moving to main concepts of electrostatics, we'll discuss something from mechanics. Some concepts of mechanics we'll be using in electrostatics. For example, vectors, Newton's second law of motion, as forces, mass into acceleration. Then measuring work, how to measure work. Then concept of energy, how work done is same as energy. So before we begin with electrostatics, we'll discuss these terms one by one. So to start with, let's discuss something from vectors. Let's have a quick revision of vectors which we have studied in 11th standard or junior classes. Okay.